They try to fill it in state.
In what?
State.
Okay, that's interesting. Okay, let me take attendance. Then let me backtrack real quick and see what, if anything, from last week's notes anybody wants details added to. And then we'll pick up with today's notes. I have a question for everybody, though. People at home, are you all listening?
Yeah.
We don't have a real strong turnout today, but I'm thinking, I'm beginning to worry about time, but I don't want to go any faster than I've been going. With all of my blended classes where I lecture from home to Zoom, the way we made up time was, rather than taking tests in class, I put the tests in Blackboard and you take them during the week at home. Is that an okay option for everybody? What I'll do is I'll just take my pencil and paper test and put pages of it in Blackboard. You don't have to rewrite the questions, just number your work and do all your work out. And then upload pictures of it to Blackboard for me and I'll grade it in Blackboard. Does anybody have a major issue if I do that for tests as opposed to making everybody take them all at the same time in the room when we don't have enough time to meet anyway?
I'm good with it.
Okay, they'll be timed, but whereas an in-class test I'd give an hour to accommodate for technical difficulties, I'll probably give 90 minutes, an hour and a half. So is that an all right option for everybody?
Perfect.
Okay, now let's see, Maria, I don't see. Anthony, I don't see. Avery, I don't see. Terrence came and talked to me. Alyssa, Romy, Latanya's here, yay! It would really disturb me if I were here and everybody else was at home. Suzanne, I'm so glad you made it in. I've been worried about you because I got a phone call from the head of our division. So, and we'll just leave it. Yeah.
Oh, okay, yeah.
Yeah. Okay. Got it. So let's see. What I need to do for folks at home is share my screen. And to share my screen, you want to right now see what's on ImageMate, what I'm projecting. And so this exam on probability with changing, it's going to be in Blackboard. And I'm going to ask you to take it between, I do not have it in Blackboard yet, but I can get it in there tomorrow because it was going to be next class, but we're doing the review sheet today. So how about if I have it available from Wednesday evening until class time next week. So between Wednesday, which will be today's the 10th? 3:10 noon to 3:16, 6 p.m. Okay, it'll be in Blackboard. You're going to just write your work neatly, number it, and upload pictures. There'll be two folders in Blackboard for the test. One will just contain the test questions. You're just going to read the test questions. The test questions will just be posted there. And the other one will be a place for you to submit your work. And I do it two separate ways because if I just give you do it as a test in Blackboard, you can only submit one picture. And if I do it with a separate Dropbox, you can submit as many pictures as you want, because I know some people like to elephant print when they do math. I need to update the attendance. Those of you who I just let in from the waiting room, because I'm running a little late anyways, can I ask you to remind me at the end of class that you were here to add you to attendance, all right?
Yes, ma'am.
Okay, so, special request to do it before we get started with the stuff for today. There was a request to
Unable to hear. Can you guys hear me now? Yes.
Yeah.
I'm
Yes.
sorry, my phone hung up. I feel so bad for the people who are actually in class, waiting patiently while I'm trying to call in to Zoom. Okay, here we go again. So we looked at using factorial last class.
I'm sorry, but if you're talking, we can't hear it again.
Okay, guys, can you hear me again?
Yes, ma'am.
I have no idea why my phone keeps hanging up. If it happens again, I don't know what I'm going to do, folks. I'm sorry. So then we use the definition of probability for basic questions. We looked at this diagram that told us that when we roll 2 dice, there are 36 possible outcomes. And we made use of that to find different probabilities. Then we talked about experimental probabilities. And we said experimental probability was usually something that we looked at from a table. And we took the number of times something actually occurred over the total number of trials. Then Ray said complementary events are 2 events that make up the whole sample space. And to find the probability of something not occurring, we subtract from 1. Then we said, for example, from a deck of cards, pick 1. What's the probability it's not an ace? We said that's 1 minus the probability it is an ace. So that's 1 minus 4 aces out of 52 cards, gave us 48 out of 52, or 12/13. So when you see that word not, you find the probability that it does occur and subtract from 1. I think we looked at using the calculator for fractions to figure that all out. Then we said probability with the word or. When you see or in probability, you add the probability of the 2 events. The only thing is, that's if they're mutually exclusive, if they don't have anything in common. If they do have something in common, the probability of A or B is the probability of A plus the probability of B minus the probability of both. And I think this is where cards makes a good example. What's the probability of getting a queen or a heart? Well, queens are 4 out of 52. Hearts are 13 out of 52. But one of the hearts is a queen and one of the queens is a heart. So we have to subtract that 1 out of 52 for that single card that we counted twice. Then we looked at the idea of odds. We said that the odds is the ratio of 2 probabilities. The odds in favor is the ratio of the probability that it happens to the probability that it does not happen. The odds against is the ratio of the probability that it does not happen to the probability that it does happen. So for an example, we said if you roll a die, what are the odds in favor of getting a 5?
I think everybody realizes that the number 5 is one of 6 on a die. So not 5 is 5 of 6. So the odds in favor are the ratio of 1/6 to 5/6. But we said that since they have the same denominators, we can just take the ratio of the numerators. Then we said 2 events are independent if one has no effect on the other, like tossing 2 coins. And we left off saying that if A and B are independent, the probability of A and the probability of B is the probability of A times the probability of B. And that was where we left off. But Latoya, that was as fast as I could do it, and I apologize. Did that fill in any of the blanks that you had? Kind of? Okay, next thing that I want to do before we start picking up from there with notes is ask if anybody wants to look at any homework questions. Does anybody have any questions on anything at all in any of the MyLab assignments? Well, I'm waiting for folks to look at the homework and see if they have questions. Today we got the penalty and not get started to know. And so we're doing the not color design. So, any questions for anybody on the homework? Okay. Homework 10. Question number 1. It's every person, when they do an assignment in MyLab, you get the same general questions, but the numbers are changed to protect the innocent. So yours will be similar, yet different. So this question says, Katrina, Maria, Eduardo, Kim, and Jim have been invited to a party. They arrive randomly, and each person arrives at a different time. In how many ways can they arrive? Does it make sense that because they're asking about the number of ways they can arrive, if order didn't matter, the question would be nonsense because they'd just all be arriving. So with this one, order matters.
No.
There are 5 of them, and we want all 5 of them to come. So does it make sense that that one would be 5, permutation 5, and that turns out to be, I believe, 120, but if you trust my old brain doing that in my head, you're a brazen. Not this one, a different one? Or do you want the second part? And how many ways can Katrina arrive first and Jim last? Is this like the question you have or no? So first, these questions are the ones where we want Katrina first and Jim last, and there are 5 people. So we've got 5 people. Katrina's first. How many Katrinas are there?
1.
1. Jim's last. How many Jims are there? 1. So we've used up 2 of our 5 people. How many are left?
3.
3. Now how many are left? 2. Now how many are left? 1. Counting principle tells me to multiply those. So there's 6 ways in which Katrina can arrive first and Jim last. All right? So now part A, and how many ways can they arrive? 120. Yay, we did it. Katrina first and Jim last, 6. Yay, we did it. So now what's the probability Katrina will be first and Jim will be last? It's a fraction, 6 over 120. But if I put that in, they're gonna say, no. They're gonna say, I got it right, but I didn't reduce. That fraction will reduce to 1/20. Okay, better one? Okay. Does anybody want to look at any others? We can take as long on the homework as you guys need. Can I ask you all to do me a favor? If you're doing the homework and you're not sure, do not stress. Over here, do you see where my little hand is waving on the screen? Question help? Please ask my instructor. It sends me an email and I will reply, unless you reply kind of sort of when I'm like in that witching zone where I'm asleep on the couch. I will reply within at most 6 hours. I usually don't sleep more than 6 hours. Usually I reply much sooner. When I reply, if it's something where I know typing out doesn't work, my phone's got a touch screen, I get attach a handwritten document, which most students find easier to read. And if that doesn't make sense, reply to that and tell me you need me to meet with me to go over it. I'll set up a Zoom meeting, all right? I don't want anybody to stress or lose sleep over homework, okay? Promise me?
Yes, ma'am.
Does anybody want to look at any other homework questions from this homework or any other? I'm sorry, I can't hear you. You good? Okay, then I'm going to go back to my document camera. And so at home, I just handed out a worksheet that's available for you in Blackboard. And we're going on what we had said last class, if we have independent events. Yep. People at home want to see what's on the document camera. If we have, sorry about that, folks, independent events, INDEPENDENT events, where the occurrence of one does not affect the occurrence of the other. We said that if A and B are independent events, and I think this was the last thing we wrote last class, the probability of A and B is equal to the probability of A times the probability of B. And if they're independent, we're just going to multiply the probabilities if we want them both to occur. Counting principle tells that too, right? With the ands, we're going to multiply. So in general, with the ands, we're going to multiply. And so now I'd like to look at these problems on this handout. People in class who have the handout in front of you, so you don't have to worry about how far I'm zoomed in. People at home, can you read that?
Yes.
Okay, so it says, you deck a card, you draw one. After you pick your cards, though, you give it back, and the deck gets shuffled again, and you pick again. And since your card is being put back in the deck and shuffled, the two are independent of each other, right? They don't have any influence at all. So what's the probability that you pick a picture card first and a heart the second time? So let's see, our picture card. It's been one of those days, I'm sorry, folks. Our picture cards are ace, jack, queen, and king. They're all considered picture cards. And so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 picture cards. So the probability of a picture card is 16 out of 52. And multiply the probability of a heart. Well, if I counted across, there are 13 hearts out of the 52. And so I've got 16 over 52 times 13 over 52. And you can multiply those fractions with your calculator if you're so inclined. I'm going to go 16 ABC 52 times 13 ABC 52, and I get as my final answer 1/13. Can everybody get that product using a calculator? Without a calculator, I'm kind of old school. I would have gone 13 goes into 52 4 times. 4 goes into 16 4 times. 4 goes into 52 13 times, and it would have taken me to the same place. But I'm guessing that you guys are more comfortable using your calculators than crossing numbers out. Did you get the 113? Did you get the 113? Okay. So let's find the probability of getting a 3 each time. In my deck of cards, there are 4 3s. So the probability the first one is a 3 is 4 out of 52. If we want a 3 each time, can we think of that as getting a 3 and then getting a 3? The word and tells me to multiply. The probability of getting a 3 the second time is also 4 out of 52. And if you multiply and reduce, I think in simplest form, that gives me 1 over 169. Now here's the dealio, folks. My math lab is going to have you stress about reducing. We just saw when I did that homework problem, it yelled at me. I had the right answer, but I didn't reduce. On the pencil and paper test, I am testing on what I taught you, which is not probability. I didn't teach you fractions. So on the pencil and paper test, if you multiplied that and got 16 over 2704, I won't fault you. I won't take off for it not being reduced, all right? On the pencil and paper test, what I'm looking for most is that you knew to multiply those probabilities. That's part of the question, the 4 over 52 times the 4 over 52. Are we all comfortable with it? Folks at home, are you comfortable with it also?
Yes, ma'am.
Yeah.
Yep. Okay, then we start getting into the weird problems. They're not really that weird, but let's look at question 25 on this sheet. Actually, you know what? I like the numbers better in 26. Let's look at 26. It's the same question, just different numbers. It says that the probability that a region prone to flooding will flood in any single year is 1 out of 10, 1/10. What's the probability that it floods 2 years in a row? Now, I have to think about this. If I got a flood last year, does it affect whether I get a flood this year? Or is each year independent? This year's weather is independent of last year's weather, right? And so we're going to look at that as the probability of a flood in the first year is 1/10, and a flood in the second year is 1/10. And so when I multiply, that'll give me 1 over 100. Does it make sense that the weather in those 2 years are independent of each other? So then what's the probability of flooding for 3 years in a row? I'm looking at a room full of intelligent mathematicians. 3 years in a row, wouldn't we do?
1/10 times 1/10 times 1/10.
So that'll give me 1 over 1,000. We're good?
Yes.
Next one says, what's the probability of no flood for 10 years? Now, this I got to do a little bit of thinking. If the probability of a flood, how do you spell flood, is 1/10, wouldn't the probability of no flood, wouldn't that be the complement, or 1 minus 1/10, or 9/10? Does that make sense? 1 out of 10 years I get a flood, so 9 out of 10 years I don't. So if I want no floods for 10 years, well, wouldn't that be 9/10 for the first, 9/10 for the second, and the third, and the fourth, and I'm getting tired of writing this. Does it make sense that that would be 9/10 multiplied by itself 10 times? So I think at this point in time, we're going to change it into a decimal. If I take parentheses 9/10 and raise it to the 10th power, I get something crazy like 0.3486. Does that part make sense? Now, where it gets a little tricky is over here. What's the probability of flooding at least once in the next 10 years? What does at least once mean? 1 or more. So I could have 1 flood, or I could have 2 floods, or I could have 3 floods, or I could have 4 floods, or I could have 5 floods. And basically it considers every possibility, doesn't it?
Yes.
Acceptable. Isn't that every possibility, at least 1 flood, isn't that every possibility except for no flood? And so I'm putting this problem aside for a minute, and back in the notes, I want to make note of the fact that the probability of at least once will always equal 1 minus the probability of none. Because at least once covers every possibility except 0 happening. So, what does that have to do with the question we were in the middle of when I told it away? What's the probability of at least once in the next 10 years? Well, that's 1 minus the probability of none in 10 years. And amazingly, didn't we just find the probability of none in 10 years? So this is going to be 1 minus that last answer, which I think subtracts to 0.6514. But somebody check me because I just did that in my head and I probably shouldn't have. Yep. 1.3? Okay. I'm just with my calculator. I'm going 1 minus 0.3486. Okay, my calculator does give me the 1.4. I'm using the rounded answer. Okay? So if you see that those words, the probability of at least once, remember, it's 1 minus it never happening. Okay? At least once is the complement of 0 happening. I promise you'll see that in the homework. I promise you'll see that on the review sheet. And I typed up the review sheet with the test open. Kind of like my math lab, same questions, but the numbers have been changed to exactly innocent. So, All right. Then, I need to give you a little bit more notes before we look at those questions at the bottom. Because if I look at those questions at the bottom, it says in exercise 33 through 36, you're going to return to a box of chocolates. There are 30 chocolates in the box, and they're all identical. 5 of them are coconut, 10 of them are caramel, and 15 of them are solid chocolate. You randomly select one, and eat it. Then you pick another. And this idea that if I select one and eat it, they're not independent anymore, are they? Because the probabilities aren't the same, because there aren't 30 left in the box anymore. And so we have to introduce a new notation. If A and B are not independent, we write the probability of B/A, and that means the probability of B given A already occurred. And we'll say that the probability of A and B, we're still going to multiply the probability of A times, it's not going to just be the probability of B, but rather times the probability of B given A occurred. What the hell is all that gibberish about? I think the candy example, and we can also make up a couple of card examples if you want. Yeah, let's do a homemade card example first, okay? Oh, no. Yeah. I wrote that on the wrong page, so I have to remember that this is where we'd start tonight. I'll put a bookmark in. Does anybody use the notes that I scan in at the end of the night? Okay, and they're clear enough for you? Okay. I use the copy machine in the division. Is it okay to turn the page over? Great. So let's say, for an example of this, we have a deck of cards. We pick one. We do not replace. Pick another. What's the probability? They're both, let's say queens. We have a room full of ladies today, we're all queens. So because they're not being replaced, the two events are not independent. And so I have to find the probability that I get a queen on the first one. Okay, my deck of cards, how many queens are there? 4 out of 52. 52, not 5. And we want the probability that we get a queen given we got a queen. Well, we've got a queen in our hand. Are there still 4 left in the deck? No, how many are left? Yes. Are there 3 queens left? We picked one of the queens, so now there's 3 left. And because I picked one of the cards, now aren't there just 51 left in my deck? Yeah. And so when we multiply that, we get 12 over 52 times 51 is 2652. And when I take 12 and put it over that, is a simple, I just did that all wrong because I'm rushing. 12 over 2652 simplifies to 1 over 221. And you see, conditional means it's not going to be 4 out of 52 each time, because that one's gone. And that's where we go. With this candy question. Again, we're going to that box of chocolates, 30 in the box. They all look the same. 5 of them are coconut. 10 of them are, would you guys say caramel or caramel? Doesn't matter. Okay, caramel's less enunciation. I am lazy. And 15 on solid chocolate. You pick one, eat it, yum, 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 and then pick another. What's the probability of getting 2 solid chocolates in a row? But what's the probability that the first one's a solid chocolate? How many solid? Beautiful. And damn it, that first one was delicious. I want another. What's the probability that the second one's solid chocolate if I already ate one? 14 out of how many are left in the box? 29. And so I'm kind of old school. When I multiply those, I recognize that 15 out of 30 is a half times 14 over 29. And I know that's going to give me 7 over 29. However, if you don't want to do it that way, use your calculator, put in that fraction 15 over 30 times, put in that fraction 14 over 29, and you should get 7 over 29 as your reduced answer. Again, on the test, I'm looking for this. And on the test, I won't sweat it if you don't reduce, because again, I'm looking for you to know probability more than arithmetic with fractions, but my lab wants it reduced. So I wrote too big to do 34, so I'll look at 35. Bless you. There isn't a box of tissues in the room. There's these things, but I don't know that I trust them. Okay. Coconut-filled chocolate, followed by a caramel-filled chocolate. So, original box has 30 in them. Of those 30, how many are coconut? 5. Oh, yum, 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 yum. We ate that coconut. It was good. But what we ate was a coconut, right? So now what's the probability of getting a caramel? Well, how many caramels are still in the box? 10. But how many candies are still in the box?
29.
29, because we ate one. And so when I multiply that, let's see, 10 goes into 33 times, gives me 5 over 29 times 3, I think is 87, but you're brave if you trust me doing that.
Yes.
Is that reducing it, folks? So this idea of when they're not independent, the probability of one knowing that the other one occurred. You good? Okay, great. Then last thing we have to do before we look at expected value is the idea of conditional probability. And I know I'll be looking at conditional probability if I see the word given. And if I see that word given, I restrict my sample space. To the given condition. So what's that all about? We flip and look at the back side of the handout. Let's look at these pretty colored discs. It says in exercises 49 to 56, the numbered discs shown are placed in a box, and one is selected at random. Question 49 asks, what's the probability that I get a 3 given a red disc is selected? So all I want to consider, I'm restricting to the red. So when I figure out that probability, how many of my discs have the number 3 on them? I think there's only one with the number 3 on it. But how many are red? 5. And so if I know that it has to be red, I'm only going to look at the red one. And so that, given it's red, is telling me to only look at the red ones. So what's the probability of getting a 7, given that I'm only looking at the yellow ones? There's 1, 7, out of how many of them are yellow?
3.
What's the probability that I get an even number, given that it's yellow? Again, here, I'm only looking at those yellow ones.
2/3.
2 out of 3?
Yes.
Now I want to look at question 53, and I've already scribbled all over the sheet of paper, so let me find another color to scribble more. This time, the question asks me, what's the probability that I get red disc, given that an odd number was selected? So red would be, say that again. 3 out of 5 is the probability of getting an odd given it's red. This time, because it says given it's odd, I only want to look at the odd numbers. And so if I'm only looking at the odd numbers, does everybody see there are 4 odds? Mm-hmm. And of those 4 odds, how many of them are red?
3.
And do you see how you really have to read carefully if it says given an odd? In my mind, I'm crossing out everything except the odd number. As opposed to if it says given a red, in my mind, I'm crossing out everything except the red one. And so those conditions matter. So let's go down and let's look at that empirical probability question at the bottom, one of those table ones. And I'd like to look at a few of these. So this is, and again, I think this data is real data. I think it's from somewhere around 2002. I think that was when the book was first written. It says, this is the marital status of the American population ages 18 or older in millions. So we've got it broken down into male and female, those who were never married, those who were married, those who were widowed, those who were divorced, and then the total number of men, the total number of female, and the total number of people altogether. If one person is selected from the population described in the table, find the probability expressed as a decimal rounded to 3 places. So hallelujah, we don't have to reduce fractions, but we got to change them into decimals, right? That the person is not divorced. When I look at this question, what jumps up and bites me on the nose is not. Remember we said when we see that word not, we're going to take 1 minus the probability that they are divorced. And I see that word not, the probability of something not happening is 1 minus the probability that it did happen. So that gives me 1 minus, let's see, how many divorced people are there? 22.8 million out of the whole group, 235.8 million. And I should be able to type that right in my calculator. 1 minus 22.8 divided by 235.8. And to the nearest 3 decimal places, is anybody else getting 0.903? Or did I type it in wrong? Is that what you guys are getting? Okay.
You're shaking your head. Okay. Yeah. Oh, okay, so I'm guessing that you got 0.097. Now, you have to subtract it from that.
Okay, great. So now, let's look at 63, the probability that somebody is widowed or divorced. Key word here is or. Remember that word or tells us to add. So this would be the probability that somebody's a widow plus the probability that somebody's divorced. Widowed is at 13.9 out of the 235.8 million, plus divorced is 22.8 out of the 235.8. But now I want to stop for a minute and make sure with that word or we have to be careful. Is there an overlap? Is there anybody in the widowed column that's also in the divorced column? No, they're independent. So we can just add those. And so I'm going to go 13.9. Oops, I got to clear what was in there. 13.9 divided by 235.8 plus 22.8 divided by 235.8. And that gives me, I would round that to 0.156. As I show my calculator display, everybody remember if I'm rounding to 3 places, I have to look at the 4th place. And because the 4th place is 5 or higher, we're rounding up. Did everybody else get that same 0.156? Yeah? Suzanne, did you get that too, hon? Okay, let me give you a minute. I'll give you a minute. I'm taking the water break. Sure. Oh, no, this is fine. And it's going to be here, you're putting it down. You're doing it to that, use division line, okay? Because they don't like in our gravity. Okay, everybody at home get that?
Yeah.
Okay, thank you. For a second, I was terrified that you couldn't hear me again. My phone didn't hang up on you. I'm so sorry my phone did that before. So let's look at 65. The probability that somebody is male or divorced. So that's the probability that they're male plus the probability that they're divorced. But this time, let's look at the table. These are all the men. These are all the divorced people. Do you see this time there is an overlap? We've got divorced men. And remember, if there's an overlap, we have to subtract that out. The probability that I have a divorced man. The overlap. So, male is 114.5 out of the 235.8, plus divorced is 22.8 over the 235.8, minus, we're going to keep the denominator 235.8, but don't we have to subtract the overlap, the divorced men, or 9.6? It makes sense to me because I wrote it. Does it make sense to everybody who heard it? Does everybody else see that one group of people is getting counted twice, and we don't want them to?
Yes.
So we're going to take 114.5. Actually, I'm lazy, and I add and subtract the numerator, hit equals, and then divide it just by the denominator. So I'm going to put in 114.5 plus 22.8 minus 9.6. I'm going to hit equals to see what that is, and then divide it by the 235.8. And I get 0. I have to apologize. I'm short enough that at that angle, I can't read it. 542. Is everybody else getting that same decimal?
Minus divorce.
And then next, I want to look at 67 and 70. Initially, they look pretty similar, but they're different. 67 asks, what's the probability it's a male, given that person is divorced? And so over here, where it says, given that person is divorced, it means I only want to look at the divorced people. And so if I'm only looking at the divorced people, my sample space is 22.8. And of those 22.8, does everybody see 9.6 are men?
Yes.
So I'm going to take that 9.6 and divide it by 22.8. And that's going to give me 0.421. As opposed to next question initially reads very similarly, but it's rather different. The next question says, number 70, what's the probability that they're divorced, given it's a man? And so over here, because it says, given it's a man, this time I'm only looking at the men. And so if I'm only looking at the men, my total is a 114.5. And of those men, 9.6 million are divorced. And you see how well the words are almost identical? Reversing the order makes a significant difference. That part that says given, that's our sample space that we want. So when we take that 9.6 and divide it by the 114.5, I get 0.084 when I round. And I want to tell you something. I use highlighters because I've got them with me. But when I look at a conditional probability question, I focus on that given part, and I circle that row or circle that column to help me remember I'm only considering that part. I am not too proud to use colors. They help. So this idea of conditional probability, when you see the words given that, are we all right?
Yes.
We're not looking at everybody, just the people who fit that definition. People at home, are you all right with it?
Yes.
Okay, then let's take a 2-minute break so I can tweak attendance. If anybody has to run, powder their nose, they can. I might do that after I tweak attendance. And because when we get back, we're going to be, you know what, to tweak attendance, I didn't need to do that. I'm doing attendance on my Chromebook. So what I do need to do, though, is look at who is here. So Maria Bernie, are you here? Anthony Carpenter, I see you. Thank you for being here. Avery? Avery, are you with us, hon? Lance? And we got Alyssa? No, Alyssa? Well, Romy? Did I see Romy enter the room? No. Morgan, you're there. Hi, Morgan, how are you? Karen Treat, I gotcha. Spencer? No. Isaiah?
Here.
Thank you. Kelly?
Here.
Yay, thank you. Suzanne, we got you. Nasla, we got you. Francesca? All right. Then, the last section of the textbook deals with something a little bit different. Kind of like a little bit of metal under the building for me. Last thing in the chapter is the idea of expected value. And then we'll talk about the expected value of an event. It's like the average of the outcomes over time. Now, my blended section didn't miss a week because they were not affected by CTI Day, that multi-purpose day where the campus was closed. And so somebody was sending me questions over the homework, a weekend with homework about these. And it's because in my labs, it's a slightly different approach. But she said that she likes the approach that we took in class better. I think it's easiest to find by making a table. When you make this table, in the first column, you list all your outcomes. What can possibly happen with this experiment? In the second column, you list the value of each outcome. every once in a while, those two are the same. So sometimes those are the same column. And we'll look at that with our first example. Then the third column, we put the probability of the outcome. And because we're supposed to have been listing all of the outcomes, that column should add to the number 1. I do have to apologize though, in the project, sometimes they don't quite add to 1, but it's pretty gosh darn close to 1. It won't add to 1 if you round it off. Like if we were using our calculators to get the probability, if we rounded all of them, it might not add to exactly 1. And then the fourth column, I'm going to put the product of the value times the probability. And the expected value is the total of that last column. So, folks at home, again, there's a folder, handouts in Blackboard, and it has this packet that I handed out in class. It's just a whole bunch of examples. And because they're mostly word problems, I took the liberty of pre-printing them. So I'd like to start looking at this first one, example 3. It asks you to determine an insurance premium. It says an automobile insurance company has determined the probabilities of various amounts of claims for drivers ages 16 through 21, and they're shown in the table. We're asked to calculate the expected value and describe what this means in practical terms. So the outcomes here are the values. This is one where the outcome and the value are the same. And so I've got the values of the claim. What's the probability somebody doesn't make a claim? I guess most people don't make a claim on their auto insurance in any given year. What if the claim is $2,000, $4,000, $6,000, $8,000, $10,000? What's the average claim? Well, we can't just add those and divide because they don't occur equally often. And so to find that expected value, we have to take into consideration the probability. So 0.7, there's a 70% chance somebody doesn't make a claim. 15%, there's $2,000, and so on and so on and so on and so on. When I look at those probabilities, because sometimes math geeks can get OCD, I always want to find the total of that column. If I add all of those decimals, what do I get? Could somebody add those for me? Beautiful. That's what we want our probability to add to, 1. So we know everything's covered. Now I'm going to be lazy and just add that last column to this table. I call it the product. And I take the value times the probability to get the product. And so I'll do the first one because it's the hardest. 0 times 0.7. Well, anything times 0 is 0. Next one, if I take 2,000 times 0.15, what do you get? Nobody's doing the multiplication for me. Beautiful. Next, we'll take the 4,000 times the 0.08. Beautiful, 320. Then we'll take the 6,000 times the 0.05. Beautiful. Then we'll take the 8,000 times the 0.01. Beautiful. And then we'll take the 10,000 times the 0.01. 100. Beautiful. And now I'm going to take the total of that column, and that total is going to be my expected value. And so that means the average claim for that age group for this insurance company is $1,100. And you see how we had it, it's kind of considered a weighted average. We have to multiply by the probability because some are more likely than others. So the expected value is $1,100, and that would be the average claim. And so if the average claim is $1,100, how much should the company charge? They don't want to lose money and they don't want to gain money. They want to break even. Does it make sense if the average payout is $1,100? They should charge their customers $1,100. So, that having been done, can I scooch my paper up and look at example 4? Example 4 says you are a realtor considering listing a $500,000 house. Realize this book was written in early 2000, so $500,000 was a big deal for a house. Not so much so anymore, depending on where you live. The cost of advertising and providing food for the other realtors during open showings is anticipated to cost you $5,000. So no matter what happens, if you're doing this listing, you're going to end up, it's going to cost you $5,000. This house is quite unusual. You're given a 4-month listing. If the house is unsold after 4 months, you lose the listing and you don't make any money. But doesn't that mean we're out the $5,000? Correct. You anticipate the probability you will sell the house all by yourself is 0.3. And the probability that another agent will sell your listing is 0.5. And the probability that another agent sells it is 0.2, I misread. The probability that the house is unsold is 0.5. If you sell it all by yourself, you make $30,000. If another realtor sells it, you still make $15,000. Bottom line, you're not going to take the listing unless you earn $6,000. Should you do it? And so that anticipated earning, we're looking for that expected value. And when I think expected value, I think table. So what are the outcomes? What could happen here? You could not sell it. You could sell it, or somebody else could sell it. And as you see, the grammatical way in which I fill that in, you're glad I teach math and not English, but you get the picture, right? So what's the value? If you don't sell it, not only do you get $0, but you don't have to pay $5,000. And so isn't the value negative $5,000? Now, if you sell it, you make $30,000, but you had to pay out $5,000. So wouldn't the actual value to you be $25,000? And in the same way, if somebody else sells it, you make $15,000, but you had to pay out $5,000, so the actual value to you is $10,000. First we list what can happen, then we list the value. In the preceding example, the outcome was the value. Doesn't happen often, but it does sometimes. Now we want the probability. And so up there in the middle of that paragraph, what's the probability that the house does not sell? I think 0.5. The probability I sell it, or you sell it, is 0.3. The probability somebody else sells it is 0.2. And doing a quick visual check, that adds to 1, so we're covering all the bases. We've got everything there. And now I'm looking for those products, which is the value times the probability. Realize this is a negative number. If you're not that comfortable with a calculator, realize when you input a negative number, you use this negative sign in parentheses. So when I take negative 5,000 times 0.5, you get negative 2,500. If you take 25,000 times 0.3, I think you get 7,500. And if you take 10,000 times 0.2, I believe you get 2,000. And so now I'm going to take the total of that column. Realize that one number is negative. I believe that totals to 7,000. And so that's my expected value. If all I did was list houses like this, average, I'd earn $7,000 for each listing. Sometimes I earn 30, sometimes I lose 5, but over time, the average, I'd be making $7,000. Make sense? Okay. Then, turn up.
So for income perspective,
if there's a cost involved, yes. Okay, sometimes up here, we didn't have to, there was no cost involved. Down here, we do. Okay, let's see. I think I'm gonna skip the next two and look at on the third page, there's a check 0.5. The one on the test is going to be similar to this, but they're much more generous than I am. They give you the table and the probability. On the test, I'd just give you the words, and you'd have to go from there. So it says, a charity is holding a raffle and sells 1,000 raffle tickets for $2 each. One of the tickets will be selected to win the grand prize, yay, $1,000. Two will be selected to win consolation prizes of $50 each. Fill in the missing column in the table, then find the expected value if you buy one raffle ticket. Describe what this means in practical terms. What can you expect to happen if you purchase 5 tickets? So, I want to, for a minute, focus on those probabilities to make sure everybody understands where they came from. Why would the probability of winning the grand prize be 1 out of 1,000? There's one winner out of 1,000 tickets. The consolation prize would be 2 out of 1,000 because there's 2 consolation prize winners out of that 1,000 tickets. So altogether there are 3 winners. And there were 1,000 tickets sold. So does it make sense that there are 997 people who do not win? And that's where that 997 out of 1,000 comes from. Now, when I fill in this table, because I want to, sometimes I have to think about it and think, all right, do I have to subtract something? If I don't win anything, am I breaking even or am I out money? If I don't win anything, am I breaking even or am I out money? I'm out the $2. And so because winning nothing means I'm losing $2, that's kind of my way of thinking, okay, so I'm going to subtract $2 from the prizes. So the consolation prize, well, it's $50. I'll actually only realize $48. And the grand prize, well, it's $1,000. I'm really only getting $998 because I had to put $2 in there. And now I call this last column the product. And I take the value times the probability to get the product. And because this is money, I'm going to treat it like a decimal. So if I take 998 times 1 over 1,000, I get 0.998. If I take 48 times 2 over 1,000, I think I get 0.096. And then if I take 997 times over 1,000 times -2, I get -1.994. And so now when I take that -1.994 and add to it the 0.096 and the 0.998, I get -0.90. And so that would be the average winning. One person earns a lot, wins a lot. 2 people win a little bit, and most people are out. And so does it make sense that the average expected value is negative? We could try to put a positive spin on it. If it's a charity, from the charity side, they're giving out these and they're winning these. The signs are reversed. So can we say that the charity earns 90 cents for each ticket it sells? They make 90 cents. So Let's look at do one more. Yeah, let's do the spinner on the wheel of fortune. Question number 18. Says the spinner on the wheel of fortune can land with an equal chance on any one of 10 regions. 3 regions are red, 4 are blue, 2 are yellow, 1 is green. You win $4 if it stops on red, $2 if it stops on green. You lose $2 if it stops on blue, and you lose $3 if it stops on yellow. What's the expected value? So what could happen? We could get red, or we could get blue, or we could get yellow, or we could get green. What's the value? If I get red, I win $4. If we get blue, blue, you lose 2, I think. Yeah, you lose 3 for yellow, and you win 2 for green. So now I want to find the probability of each of those. Let's see, there are 10 regions. If 3 are red, the probability of red is 3 out of 10. What's the probability of blue? Four of the 10 are blue. 2 of the 10 are yellow. And 1 of the 10 is green. Now we're going to take the value and multiply it by the probability. Do you guys want to multiply and express your answer as a decimal or a fraction? It doesn't matter to me. Should we do decimals? 4 times 3/10 is 1.2. -2 times 8/10 is -0.8. -3 times 2/10 is -0.6. And 2 times 1/10 is 0.2. And so now for my expected value, I want to total that column. Doesn't it add to 0? Yes. And that's actually an example of what I think they usually consider a fair game. A fair game, the probability of winning is, the expected value is 0. The chances of winning and the chances of losing kind of balance each other out. Okay? But this idea of expected value, all right. That student that sent me emails over the weekend, when she did these, Help Me Solve It didn't put it in the table. And so Help Me Solve It, if you use it, showed it as 4 times 3/10 plus -2 times 4/10 plus -3 times 2/10 plus 2 times 1/10. And I just think doing it in the table and adding down just makes it easier to read. I think it makes it easier to organize your thoughts. So I would strongly suggest you use the table. But if you don't want to use the table, I guess you don't have to. But I think it makes it a hell of a lot easier than trying to type all of this in at once. Yep. So, and guess what? That is the end of this chapter. So, I am torn right now. Because I know we started out saying, yeah, we'll do the test review today, and you can do the test anytime from tomorrow or the next class. But I'm wondering, is that fair to you guys? Should I give you an opportunity to do this homework and ask questions on this homework before I give you a test? That would be what a nice person would do. So I'm thinking, this is the end of probability. Rather than doing that test review today, let's do that test review next week. And what we'll do is we'll change it so that the exam on probability will be available from Tuesday, the 16th, 9 p.m. until Tuesday, the 23rd at 6 p.m. Because I don't feel like giving you that test before you have a chance to practice the homework. Not this week, you're going to take it, but you're going to take it next week. Yes, after the 16th. We're going to put, initially it was going to be class time on the 16th, and we were going to do the review today, but I'm thinking, I think I want you to practice first. So what I will do is that I give you practicing first. Is if you're in class, I'm giving you a printed out copy of the review. If you're at home, people at home, can you still hear me? If you're at home, there's a copy of the review and then handout section of Blackboard already. And so, you still have almost an hour's time left. So even though, rather than doing that review now, I'm going to do a little bit of introduction into the next section. Before we do that, should we just take like a 5-minute mental health break? Okay, so let's reconvene on my itty bitty watch, it's 20 of, so let's reconvene at 1:15 and let's take a quick 5-minute break, okay? So I will be back in.
feel like I'm yelling to be heard through the mask. Does anybody else need a hall, want a hall? You don't need a hall. You don't need a hall. Oh, the doctor. You want a hall. Okay. Okay. I put Rob really good athletes, and they didn't get it from me. It's in the record, okay, that it's for me. Oh my goodness. My daughter was such a good softball pitcher. Katie was maybe 11, and she was at a pitching clinic, and the coach set up a home, like he did say this home. And she was able to hit the ball, like curve to the throw a ball that curves to the cone. Your daughter is a pitcher? Both of my daughters. I think she was 10, and I was catching for the red play. And I missed the ball, and this one red she threw so hard.
My daughter lost softball too, but he got a little shot at the time. She was like 15, well, 14 or 15, and we were practicing in front of the house, and I had the dog out there just tied up. And she threw the pitch, and she accidentally hit the dog right in the eye there, and it was awful. Yeah, and she was dying and everything, but.
Who did she play for?
She played for football, never was high school.
Okay.
I love softball, though.
Did she play travel ball?
Well, she's 21 now, so she.
When she was a kid, did she play travel? No.
You know, my husband coached football, my boys were in football, so it was so much, it's a big commitment.
Yes, it is.
But
Yes, it is.
what else, I played football.
Mm-hmm. Yeah, both my girls played travel ball and school ball. So yeah, they played for Amherst Central School District. Yeah. So.
Yeah, very nice.
My son played baseball, but he wasn't as good as in baseball as his sisters were in softball. But when he was in high school, he found his niche. He became a distance runner and ran cross country, indoor track and spring track, but like the mile or the 2 mile or whatever. And 1 week he was the Buffalo News Runner of the Week. So it was, yeah. And God bless them, they got that from their dad. My sport is couch potato. You know, the worst you can do is hurt your thumb with the remote, and then you use the other hand for a while. I was like, once when they were playing T-ball, they said they needed a coach where I coach, and I looked at them and said, honestly, if I see a projectile coming at me from the air, I run into it. You don't want me coaching. Oh my heavens. It's like the girls play volleyball too. And they like throw themselves on the floor and I'm like, no, run and hide.
My daughter loves it like 7 too.
Okay.
So I think sometimes, but they're
Yeah. My sport is spectator. So, with expected value, we're done with probability. You will have an expected value project, but I don't feel like handing out that project until you have time to practice. So I will also give you that project next week, because this project is a little involved. You'll probably have a book. Okay? But with your projects, what you're going to do is you're going to go to the New York State Lottery site and pick a dollar game and figure out what the expected value is for that game. I thought it might be interesting. I don't know. So. Okay, so statistics. That's chapter 12 if you're working from a book. In the real book or in the virtual book, I'm going to ask that you please read chapter 12,
section 1. There's some cool stuff in there. There's, I'm sitting and thinking, there's a story that I should have dog-eared in this book that I'd like to have you peruse at some point in time tonight when we get to the idea of random sampling. So, it's statistics. You've heard of it. When we talk about statistics, what are we talking about? Anybody at home have an idea? Yeah, it's the study of data. And so when I look at statistics, it's really broken down into 2 parts. The first part is the descriptive statistics. And I'm tripping over my tongue. I'm sorry. Descriptive statistics includes collecting, organizing, representing, and summarizing the data. We're going to come up with something that we're interested in. We're going to go out, we're going to collect all this data. And we have this big pile of information, which does nobody any good if it's just a big pile of information. So I need to take that information and I need to organize it. I need to make it into a chart. I need to make it into a graph, something that summarizes it and shows people what the data is. And then I need to come up with descriptions. What's the middle of the data line? What are the extremes of the data line? And then there's inferential statistics. That's where we use descriptive statistics. I can go out and come up with all the statistics and make it all look pretty and tell everybody all about it. But don't we usually want to take that information and generalize it and use it to draw conclusions? And so inferential statistics, we're going to use the data to generalize and draw conclusions. Originally, this class, Math 106, was written to help people gear up, people who didn't have quite that rigorous background in math for statistics class. And so we're kind of, if you're taking a statistics class, this is supposed to help you in that math class. We're going to spend more of our time on descriptive statistics. In a statistics class, the descriptive statistics is the tip of the iceberg. About a third of the semester is spent on that. And then the rest of it is the inferential. We're going to go out, it's the idea that when people do statistics, you gather all of this data, but then you use it to draw conclusions. So when we look at collecting data, we talk about a couple of different groups. The first group that we talk about is the population. Population. Sorry, does anybody else, did your spelling skills get weaker as the day carries on? I apologize. The population is the set of everything being considered. So I might be doing a study about American college students. And so the population would be all of the college students in this country. Or I might be doing a study on American-made cars. And so then my population would be the set of all of the American-made cars. So example might be all U.S. college students. So I want to do a study of American college students. And so I get this testing question. I want to know how many college students love math. And so I want to know about all of the college students in this country. Is it feasible for me to run around and ask every college student in this country a survey about math? I think by the time I finish just surveying the college students in New York State with the number of colleges in the state, I'd have to start all over again before I go to the next state because it would be 4 years and everybody would be out of school already. It's just not feasible. And so instead, we usually look at a sample. And a sample is going to be, hold your horses, your favorite word in the world, a subset of the population. And so usually if I do a study, I'm going to not necessarily approach the whole population, but rather a subset of that population. Because it's usually not feasible to reach out to the entire population. What my subset is really depends. We want to look at what's considered a random sample. And a random sample is defined as a sample in which every member of the population has an equal chance of being selected. And there's all sorts of different ways of getting a random sample. Let's say instead of wanting to look at all the college students in the country, I wanted to look at like the population with all the college students in entrance. I don't have access to all the students in entrance. Would it be a good sample to get these people in this class? Would the people that take contemporary math be representative of all of the college students? No. It would be a biased sample. It wouldn't be fair. Instead, a random sample, an ideal way would be to put all of the names in a hat and pick out all of the names. Can't do that, so maybe I'll go over to the registrar's office and have them give me a list of all of the students and pick every 100 ones on the list where they're randomly selected. A couple of examples of bad sampling techniques. I must be getting old. My kids are getting old. Are any of you old enough to remember way back when President Obama got elected the first time? And Obama ran against me. And the night before the election, the day before the election, everybody was like, oh my God, it's too close to call. Oh my God, it's too close to call. Oh my God, it's too close to call. My son was a political organizer, and he worked on the Obama campaign in 3 counties in Indiana. And he kept saying, Mom, it's not too close to call. Obama's going to win. And I'm like, but on the news they say it's too close to call. And he said, yeah, but the reason it's too close to call, this was back in 2008.
yes, because they're only calling landline phones. And in 2008, who used a landline phone? Old people. Everybody under the age of 30 didn't have a landline phone anymore. And so it was a bad sampling technique, right? They only asked people who had landline phones, people who were older. This was an example that I wanted to pull out of the book it also deals with. It says, in 1936, the Literary Digest mailed out over 10 million ballots to voters throughout the country. The results poured in, and the magazine predicted a landslide victory for Republican Alf Landon over Democrat Franklin Roosevelt. I think there were places that, based on this survey, newspapers had the headlines, Alf Landon wins. Did we ever have a president, Alf Landon?
No.
No. Did we have a president, Franklin Roosevelt?
Yes.
Yes. How did they get it so wrong? Because they only mailed out ballots to their subscribers. Think 1936, that was just after the Great Depression. Could most people afford a magazine subscription, let alone a literary magazine subscription? And so it was a biased sample. It wasn't a fair sample. And so there's a lot of stuff in the textbooks that deals with that idea of fair sampling. And so that's why I'm asking you to read the first chapter, because it's interesting. Types of questions on fair sampling that you'll ask, I'll ask on the test and you'll see on the homework. If you look over here, exercise set 1, it says, the government of a large city needs to determine whether the city's residents will support the construction of a new town. The government decides to conduct a survey of a sample of the city residents. Which one of the following procedures would be most appropriate for obtaining a sample of the city's residents? Survey a random sample of employees and inmates at the jail. You think that would be unbiased?
No.
No. Survey every 5th person who walks into City Hall on a given day. Does the average person walk into City Hall?
No.
No. That's not unbiased. Survey a random sample of persons within each geographic region of the city. So I'm going to take the city, divide it up into neighborhoods, and survey, a couple hundred people from each neighborhood. That might work. How about survey the first 200 people listed in the phone book?
No.
No, first 200 people listed in the phone book probably all have the same last name and they're probably all related to each other, right? And so does it make sense that the best choice here would be C?
Right.
Yeah. We could spend hours and hours talking about sampling techniques, and it's interesting, but you could spend hours and hours. One thing I want to add is the idea that a self-selected sample is not good. One of the news channels that my husband, when he was used to work, we watched the early morning news, and they always said, we have, excuse me. We're voting on the best pizzeria in Western New York. We're voting on the best this in Western New York. We're voting on the best that in Western New York. And it blew his mind when the best pizza in Western New York was some pizzeria in Springville. Did that pizzeria in Springville have the best pizza in Western New York? No, but did they have the most relatives who called in and said they were the best? Sometimes do you ever get like the flyers in the mail from your politicians and they say, we care about what you think. Check. And do you guys mail those back? No. Who mails those back?
says the politician, people with extreme views, you know, senior citizens that are sitting at home and have nothing else better to do. Do you think that those responses that they get mailed back really represent what people want? No, because people get to decide if they respond or not. And I think that's part of the problem with some of the sampling techniques with that last election. You know, there was, and even 4 years ago, the preceding election, the results were not at all what the pollsters thought they would be. Because again, when a pollster calls, people decide whether they want to participate or not. So there's all sorts of problems there. So anyways, read that first section of chapter 11 and they'll give you a lot more. You know, I think it's interesting, but let's stop with that and let's go and look at some of the more mathy part of things. And so section 2, the other part of section 1 of the chapter deals with organizing data. And so we're going to have several ways of organizing data, and you folks are going to be expected to make each of these organizational tools. So when we organize data, one thing that's always important in any way we organize our data is that we want to label everything. Every column, if I'm in a table, every axis on a graph, if I do a table, I want to make sure that it has, anything has headings, titles, because it does no good to have this great organizational tool if you can't look at it and know what it represents. So labeling is really, really, really important. The first method that we're going to use for organizing data is something that's called a frequency distribution. And a frequency distribution, doesn't that sound fancy and difficult? It isn't. It's a table. One column lists the data values. And one column lists the frequency, which is the number of that value, the number of values. Sometimes there's a tally. And now I feel awful. I'm between a rock and a hard place because every time I've taught this, when I go through and do this part and make the frequency distribution, I survey the people in class about some random thing. And, well, people at home, do you promise to answer my questions if I ask you?
Yes.
All right, so let's go through, and for our example, let's use shoe size of people in class. And I'm going to be mean and say I'm only dealing with whole sizes. You know how sometimes when you buy shoes online, they don't sell half sizes. So give me your closest shoe size. I'm going to have shoe size of people in class would be my title, my heading. My first column would be the shoe sizes. For this one, I'm going to make a tally. And then we're going to have the frequency. And does anybody have a shoe smaller than a 5? I'll take that as a no. So we'll go 5, 6, 7, 8, 9, 10, 11, 12, 13. Does anybody have a shoe size bigger than 13? I'll go first. I wear size 5. Suzanne, what size do you wear? 8? Tanya, what size do you wear? 10? Okay, now, Anthony, what size shoe do you wear?
11.
Zoom user, I forgot who that is. Somebody didn't type their name into Zoom. What size shoes do you wear?
10.
10?
Yeah.
Terrence, what size shoe do you wear? Are you Zoom? You're not Zoom. Well, we'll count you as a Zoom user too. Morgan, what size shoes do you wear?
An 8.
8? Okay. Now I have to go to the other half of the class. Oh, we don't even have that many people. Kelly, what size shoe do you wear?
I'm an 8.
You're an 8?
Yep.
And Sharon Preet, what size shoe do you wear?
Can you repeat it? Sorry.
I'm sorry, I didn't hear what you said. What size shoe do you wear?
Me?
Yeah.
I have like 7.
7? Okay, thank you. Did I get everybody? Oh, I thought there were more people in the Zoom class. Okay. So, frequency then, there's 1, 5, 1, 7, 3, 8, 3 10s, and 1, 11. So that's my organized data. Folks, that's my frequency distribution. That's really all there is to it, is making a table showing the frequency of each value. Can I turn the page? So then next is a grouped frequency distribution. And with a group frequency distribution, I don't look at individual values, but rather I put the data in classes that are usually equal width. And so this class really isn't big enough to make a group frequency distribution, so I'm going to recycle information from the previous semester. I apologize. In this example, I'm looking at exam grades for 106 class. And I liked using that example because usually this lecture was the first class after they took that test, and it let people see where they fell in the spectrum. And so when I look at the classes, I might have something like grades from 90 to 100, and then 80 to 90, then 70 to 80. But I'm going to stop there because I intentionally did something wrong. What's wrong with those classes the way I have them written? Which group would the 80 go in? Does it make sense that there can be no overlap of the classes? We don't want any number to appear in two different classes. So instead, my grades, the classes might instead be um, 90 to 99, 80 to 89, 70 to 79, 60 to 69, 50 to 59. And do you see how that way there is no overlap? And then for each grade, I would list its frequency. And so here, 90 to 99, that semester was 9. 80 to 89, that semester was 11. 70 to 79, that semester was 7. 60 to 69, that semester was 7. 50 to 59, that semester was 3. No, I have, this is information from a back semester. It was actually 2 classes combined. So when we look at a table like this, we talk about lower class limits. And does it make sense for the classes that I have that the lower limits would be the smallest number in each class? So they would be my 50, 60, 70, 80, and 90. So if I look for the upper class limits, that would be the largest possible in each class.
Can you move the paper up? I can't see it.
Yeah.
Thank you.
Nobody can see it then. Thank you for letting me know. The largest in each class. So what would be the largest class limits for this table? The upper limits.
59, 69, 79, 89, and 99.
Yeah, 59 would be the largest number in the bottom, then 69, then 79, then 89, then 99. And then the other thing that you need to be able to find from a table like this is the class width. And the class width can be defined in one of 2 ways. It's the difference between 2 successive lower limits or the difference between 2 successive upper limits. And so what the heck do I mean by that? I'm going to just take any 2 successive classes, which means classes that one follows the other. And so if I take the difference between 2 lower limits, that might be 90 minus 80, which gives me a class width of 10. I'm taking lower limit minus lower limit. And is the glass half empty or half full? We could have also taken upper limit minus upper limit. And if I would have taken 99 minus 89, that would have also given me the class width of 10. You have to be careful though with class width. You're subtracting this way. Either lower minus lower or upper minus upper. Okay? So far so good. Is it a frequency distribution? It's easier than it sounds. We're just making a table, how many fall in each group. Next display is something that I think some of you might have seen in high school, but I'm not sure that everybody did. Next display is something that's called a stem and leaf diagram. In a stem and leaf diagram, we use to organize usually 2-digit data. The stem is the leftmost digit. The leaf is the rightmost digit. We want the stems to be in order. We want the leaves to be in order. Now here, technically when you do a stem and leaf diagram, you're not supposed to put anything in between the leaves. But I think in my labs, they asked you to put a comma in between the leaves. So in my labs, you need to put that comma in between. In the statistics class, they yell at you if you put the comma in between. So I'm going to leave it up to your discretion whether you put that comma in between or not. And then you also need a key. A key is just something to explain, like the place values. So I'm going to, for an example, I'm going to use these exam grades from a previous semester. I'm not going to make them up, I'm stealing them. We went from 50 to 90. So the exam grades were 50, 50, 55, 60, 60, 60, 63, 66, 67, 67, 72, 73, 74, 76, 77, 77, 79, 80, 82, 83, 84, 85, 85, 86, 87, 88, 89. There were 2 88s, I missed one. And then 90, 91, 92, 93, 94, 2 95s, a 97, and a 99. And so, is everybody right? I've got a lot of 2-digit numbers. And we could look at that list of numbers and go a little cross-eyed. We could look at that corresponding frequency distribution, but with the frequency distribution, I use the individual value. So what I'm going to do is I'm going to make a stem and leaf diagram. Of exam grades. Does everybody see the exam grades are 2 digits? First digit is the tens place, second digit is the ones place. So my stems are going to be my tens places. So I've got 90s, 80s, 70s, 60s, and 50s. I'm moving it up, And they're in order, right? It doesn't matter, I could have gone 50s to 90s, 90s to 50s. It's personal preference as long as they're in order. Now for my leaves, let's look at the grades in the 50s. The first grade in the 50 is a 50. So I'm going to say the tens is 5, and then there's a 0, and that represents a 50. The next grade is a 50 also, so I'll put another 0 there. The next grade is a 55, and so I'll put a 5. And so you might not have seen this before, but can you picture, instead of writing all those goofy numbers out, saying, okay, so I've got 50, 50, 55. So then I have 60, so I'll put a leaf of 0, another leaf of 0, another leaf of 0. Then I have a 63, a 66, and 2 67s. Then I have a 72, a 73, a 74, a 76, 2 77s, and a 79. And you see, just like that frequency distribution, it tells me I had 3 grades in the 50s. It tells me I had 1, 2, 3, 4, 5, 6, 7 grades in the 60s. But besides telling me how many I have in each group, I can actually see what those individual scores were. It's not hard to make, and it's easier, it's more concise than looking at the great big list of numbers. So what would the row for the 80s be? I'd have 8, 0, 2, 3, 4, 5, and there's 2 8s because I forgot a number, and then a 9. And then for the 90s, we'd have 9, 0, 9, 1, 9, 2, 9, 3, 9, 4, 5, 7, and 9. And so now that I've got that diagram written, the key is going to be something like this that says we can pick any number from there. It might be that 9/0 equals the number 90. So that if somebody had never seen one before, they'd have an idea as to what it all means. The other reason we need to put something like that is because we're looking at 2-digit data, but let's say instead of being test scores, there was like home value. And so instead of being 90, that might be $90,000. And I need a key to explain this. And so stem and leaf diagrams, not difficult to make. And you don't lose the individual values, but it organizes them as much as our frequency distributions do. Sometimes you see a split stem and leaf. I got to move it back down again, sorry. With a split stem and leaf, you use it if there's a lot of values. And so if I were making a split stem and leaf, I might have 2 for the 90s, 2 for the 80s, 2 for the 70s. And this upper one might be 95 to 99, and this one might be 90 to 94, and this one might be 85 to 89. And I just, split it up, because sometimes, can you picture if I was looking at the right data, the leaves might be very, 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 very long. I think one semester, I tried to make a 7-leaf diagram of people's ages. And when I got to, everybody was either 19 or 20. And so I've got an 18, 19, or 20, 21. And so I have 1 for the 10s, and then I have 8, 8, 8, 8, 8, 8, 8, 8, 8, 8, 8, 8, and it just becomes ridiculously long. Let's see if I can split it up, just so that it fits on your paper. Sometimes you also have something like a back-to-back stem and leaf. And a back-to-back stem and leaf you'd use for comparison. And so if I were looking at those test grades, 9, 8, 7, 6, 5, I might put the women on one side and the men on the other. And so I have the leads for the women going in one direction, the leads for the men going in the other direction, and I would use it to compare. Let me double check. There's an interesting example in the textbook where they were looking at the ages of Oscar-winning actors and actresses. And they compared the actors to the actresses. And so if you look, the actresses, most of them are in their 30s, right? You have 30, 30, 31, 31, 33, 33, 44, 34, 30, most of them are in their 20s and 30s. And there are very few older women. As opposed to with men, most of them are in their 30s and 40s. And older men are more likely to get acknowledged as actors than older women, which I guess is making some sort of lead statement or another about practice. I don't know. But you see how we can do the back-to-back to make a comparison like that. Okay. Then, do you guys have enough wherewithal to look at one more type of graph? Next one, I'm thinking you might have heard of in high school. Has anybody heard of a histogram? Anybody ever hear of a histogram, either at home or in class?
Yes.
Sound it all familiar? No. A histogram is a specific type of bar graph. When I make a histogram, it's important that the horizontal axis are my data values. My vertical axis will be the frequency. In a histogram, it's important that the bars have equal width. In a histogram, it's also important that the bars touch. They meet. And like we said at the beginning, it's important that you label everything. It's also important to sometimes put a break in the axis. And so I guess we can do, it's going to have a couple more breaks in it than I would normally have, but let's make a histogram of shoe sizes of the class. So there's my title. It's going to be a bar graph. My horizontal axis is going to be my data values, so those are going to be my shoe sizes.
Can you move it up, please?
Sure. Sorry. Thank you for letting me know. Now, is everybody familiar a little bit with graphing? And when you graph over here where they meet, it's supposed to be 0. Do we really need to start at 0 for shoe sizes? No. So that's where I'm going to predict break in the axis. It's kind of like that idea of when we talk about putting an ellipsis in the set. We said it was like when little kids go, I'm going to skip a few. We're going to skip a few because we don't need any of those. And so our smallest size was a 5. And we'll keep on going, 6, 7, 8, 9, 10. I think the largest size that we had was an 11. And now this vertical axis, we can label frequency, which would be fine. I think that it would be clearer rather than saying frequency if we said something like the number of people with that size. And I think the largest frequency that we had was 3. So I'm going to just go 1, 2, 3. When I make a histogram, I want my bars to touch. So I usually center the bar over the value. And so size 5, there was 1. So I'm going to make a bar that goes from 4.5 to 5.5 with a bar of height 1. Now I know technically we said that the bars are supposed to touch, but nobody had a size 6. So we can almost picture like a flat line there, a bar of height 0 for size 6. Then we had one person with a size 7. Woo-hoo, we had 3 people with a size 8. We didn't have any size 9. We had 3 people with a size 10. And we had 1 person with a size 11. And am I correct in assuming that everybody in the room has seen a bar graph before? What's really important if you're going to call your bar graph a histogram is that the height of the bar is the frequency. If I would have drawn this sideways, it would no longer be a histogram. The height of the bar has to give me the frequency. The other thing that's important is that those bars touch. And again, if the bars are equal width, with an artistic merit. I'm not the world's best drawer. So, histogram, okay. Can we draw one more histogram or do we gotta go? One more histogram. I promise this will be the last one. Last one for the day is going to be a group frequency histogram. And with a grouped frequency histogram, I usually label the horizontal axis with my lower limits. And so because I have no pride, I'm going to recycle that data for exam grades, because that was our grouped data. And our first class was 50 to 59. So I'm going to label 50, 60, 70, 80, 90, we went up to 99, so I'm gonna go up to 100. Does everybody see the need for a break there? Because we're not starting at 0. It's gotta be evenly spaced. And our highest frequency was 11. So I guess over here for my frequency, I'm going to count by 2s. 2, 4, 6, 8, 10, 12. And so in the 50s, between 50 and 60, I had 3 papers. In the 60s, there were 7. So between 60 and 70, I'll have a bar of height 7. In the 70s, between 70 and 80, we also had 7. Between 80 and 90, we would have a bar of height 11. And then between 90 and 100, we'd have a bar of height 9. And so sometimes you see that group frequency distribution like that. And do you see how it looks like? Okay, in the 50s, there were 3 between 50 and 60. Sometimes, instead, you see people underneath the bar write 50 to 59, 60 to 69, and so on. But I personally think it looks more cluttered when you do that. I think it's a neater diagram if you just use those lower limits. And so let's stop here and call it a day because we've only got 5 minutes anyway. So there's one more graphic distribution, and then we'll start looking at measures of central tendency next week. So we look at measures of central tendency next week. We'll answer whatever questions you might have on the homework and go over that practice test. All right?
Okay.
So I think I'm going to stop sharing my screen. And this time, yay, I did remember to hit the record button. So that YouTube video